Swayam Prabha. Digital India. Educated India.
Now is actually like actually processes and how they are connected with defect mobility and how you can know all that and be yeah. And I'm not going to talk about all that in here because it would take too long. So, and we're going to try and do things together. Let's assume that I have a crystal and I have a vacancy. So I have a missing atom, and then that vacancy has free neighbors. And now you all know that for the vacancy to move, you need to have to exchange with one of its neighbors. And if we look at the energy of the system, as the vacancy is moving, so from the initial configuration, which is like this, to the final configuration where the vacancy and the atom have extend, there will be an image barrier, right? With here and into the delta E, which means that the characteristic time it will take, or the average time it will take for the vacancy to exchange with an atom will be what? So the T jump will be exponential minus delta, or sorry, it is a times of this plus delta E over KT. And then you need me 1 over a frequency, a characteristic frequency for those. So this is the classical law. Now, imagine that I put the stress on the system. I put the system in compression with pressure. What do you think is going to happen? Yeah, so the curve might be affected. And in this case, if I am under pressure, for example, I should not be looking at the energy. I should be looking at the N output, right? So actually here, instead of an E, it becomes an H. And this is a delta H. And actually, so behind, so really as this is what is called the Arrhenius law, where you have only the energy. Actually, to justify the Arrhenius law, there is a theory called the transition state theory. There's a slide for it, but I'm not going to go into it. But the transition state theory, actually here, it is not based on delta E, it is based on delta H. Actually, it is even based on not delta H, but it's based on delta G if you have a system which is at a given stress and temperature. That's what the TST tells you. Now we know that delta G was the relation between delta G and delta H. So this simply you can write it as 1 over nu, and then I have an exponential minus delta S over KT. And then I have an exponential minus delta H plus delta H over KT. Sorry, there's a T here that goes away. Most people, when they apply the transition state theory, they will say that all this is just one reference activation, one reference democracy, a whole thing here. And you will look only at how the entropy is changing. There are two reasons for that. One is that in many cases, it is true that this term is close to a constant. So that's the good reason. The bad reason is that actually, if you want to look at this term precisely, you need to compute a variation of entropy, and entropy is complicated. So the bad motivation for taking this as a constant is because delta H is much easier to compute than delta S. So let's not worry about S. But still, in practice, this is a a function actually of sigma and t, and this would be also a function of sigma and t, right? So, where do I want to go with this? Yes. So, yes. So here, so this data set. So in many cases, what you say is actually that delta S is a constant. And so you put the delta S with the frequency. And this is just a constant times this equation entropy. And so and then moreover, what many people will do is they will do a harmonic approximation where actually delta H, you drop the dependence in temperature and you drop the dependence in temperature here. So in the end, what you end up with is you have to compute an activation enthalpy, but at zero temperature. You have to do a static calculation to get the enthalpy, and that's enough for your calculation. Right? Now you can do better, but then it's much more computationally intensive. So for example, using the harmonic approximation, we can compute the entropy here. As you have, for those who know, I'm just going to full begin, you have to compute the dynamical matrix, so the matrix of the second derivatives, and you have to diagonalize that matrix. And from the eigenvalues of that matrix, you can compute that. You have to diagonalize the very big matrix, and that's extremely computationally expensive. So few people will do. Or you have methods that allow you to compute directly delta G that are based on what we call thermodynamical integration. Again, it's very advanced methods to directly get this, and it's computationally very expensive. So again, most people will take simplifications, but it's fine if you do a simplification. You just have to keep in mind that it is a simplification where you assume that you have a constant attempt frequency times the exponential of just the enthalpy. This is a list simplification, and in some cases, and we are fighting with the referee to try to publish a paper where we show that in some cases you have to be very careful with this entropy terms here. You cannot assume it's constant. Raise a hand. Exactly. So that's how you do that. Getting the GIS and computing numerically the GIS energy is difficult. It takes a lot of calculation to get G. If you are able to, if you do thermodynamical integration, for example, and you are able to compute what is the variation of the GIS energy along the transition path, then you take the first derivative and you have the entropy. So be careful, yeah, I was too fast. This would be the vibrational entropy. It's not the configurational entropy, because here there's only one configuration. It goes from here to here. So the configurational entropy, in this case, is zero. But the system vibrates, and there is a vibrational entropy, and even if I'm just looking at this guy, or when I'm at this is the initial configuration. At the saddle point, basically the atom is in the middle. Then at the end, they both have exchange, right? So this guy is moving here, it's here, and then it runs here, right? The way this atom will vibrate when there is a vacancy to its left, or how it will vibrate when it is in the middle between the two positions, the way the vibrations are done are different, and that gives you a difference in vibrational entropy. You see, but the difference can be small, or it can be large. You never know before you've done the calculation. It's hard to know whether it's small or not. It's more if it would depend on for example, on the urban stress. That would give you a dependence of this term on the stress that is usually neglected. And as I said, there are some cases with duplications. My favorite part. With the screw duplication in BCC metals, what we have shown is that this term here can vary very strongly with the stress, depending on the model you are using, the atomic potential and so on. But okay, that's so what did I want to say? So we look at the vacancy. We have the activation energy. We have the frequency, and we have already said several times that if we take orders of magnitude, just for a simple vacancy, this frequency or the characteristic jump time will be much longer than when we can afford with LG, and so we're never going to see the dislocation drop. This was my slide on transition state theory. We can move. This was my slide on the entropy. So we said the entropy is if the entropy is constant, you can put it in a time frequency. Otherwise, it can be computed using the harmonic theory. There's a very good. So there's this. In the supplementary materials of this paper that we wrote now a long time ago, we tried to explain all of this. So there's the harmonic approximation, or you can do the full anharmonic calculation using either thermodynamic integration. And there's a recent, very interesting method called coffee, which is explained in this QRL paper, and allows you to contribute the techniques. Now, what is the effect of a stress on this? Can we be more precise? Imagine that the vacancy that I have here, I model this vacancy with an eigenstrain. So I have this vacancy. It has a volume V naught, and it has an eigenstrain epsilon star, as we have discussed yesterday. Now I apply either a pressure or a stress tensor. How is the enthalpy of the vacancy changed by the application of a stress within the elasticity theory? So reduce, it will change. It can either, but you can give me a formula from what we have discussed yesterday. And I know it was dense and heavy, but actually, from what we have discussed yesterday, we can write that the enthalpy of the Defect will be its energy when there is no applied stress. And now, what will be the effect of an applied stress on the energy of the? Yesterday, we said that the interaction energy, so it can be between two defects or between an applied stress and a defect. What was the formula you wrote yesterday? You remember? There was a minus, there was an integral over the volume of the sigma of one of the defects of the second delta V. If I assume that the first defect actually creates a homogeneous stress, it becomes this. And this is now so this will be the applied stress. This is the eigenstrain of the vacancy, which is 0 everywhere except inside the vacancy. And so that integral will become minus V0, where the eigenstrain is non-zero, sigma double contracted with the eigenstrain of the vacancy, which we assume is constant inside V0. So your colleague is completely right. This is the so this would be very good. No, this would be, for example, the energy, how the enthalpy of the initial configuration varies. Now, as we are moving along the transformation path as a function of x, then we can define an h of x, which will be the energy barrier that we have with no applied stress. And now we have a minus, so V0 will not change, sigma will not change, but then there's no reason why epsilon star will be the same. Epsilon star, the eigenstrain of the vacancy, does not need to do the same when the vacancy is near the atom or when there is an atom in the middle of the vacancy. Right? So this depends on epsilon x. And it means that the energy barrier here, so if I say that the position of the maximum energy here is x star, how do I run delta H, the activation entropy? So it's going to be the delta E that I have initially with no applied stress. Then I have a minus E naught, sigma. And then I have the eigenstrain at the activated state minus the eigenstrain at the beginning. In this example, yes, because the final state is the same as the initial one by symmetry. But there are some cases where the final state is not the same as the initial state. So then you have to be careful. If the final is not the same as the initial, the activated energy is activated minus initial. Because then the barrier to go in, so that's the barrier to go in this direction. The barrier to go in the opposite direction would be activated minus 5. They don't need to be there. Do you agree with that formula? So now to have a dependence of the enthalpy on the applied stress, you need two conditions. Or let's say, so to have a dependence, this term here needs to be non-zero. For this term to be non-zero, you need two conditions. So first, this has to be non-zero. So it means that the eigenstrain of your defect has to vary along the path to have a stress dependence. If for some reason the eigenstrain is constant along the path, or is the same here and here, then there can be no, within the elastic theory, there can be no stress dependence of the enthalpy. And so you're back with just the energy barrier. So that's the first condition. There's the second condition. Imagine for the vacancy that I apply a shear stress. So that my stress, imagine that my stress is something like I have zeros everywhere, and then I have the term here, which is not 0, 0, 0. I have the same term here. This is my stress. What is the shape of the eigenstrain of a vacancy? It's diagonal, at least at the beginning. So here, not as clear, but let's assume that here it is also diagonal. The eigenstrain would be some value times 1, 1, 1. What is, how much is this product? Or what's the value of this product? It is 0, right? So not any stress might couple with the motion of the defect. In the case of a vacancy, what do we couple with it's terms on the diagonal, so it's the pressure terms, right? So the pressure has a good chance to affect, the pressure has a good chance to affect the migration of a vacancy. Shear terms less, unless there are non-diagonal terms in the equation instead. To know that, you have to compute it, right? You cannot know that equally. So the second condition, so the first condition is that the eigenstrain must vary. The second condition is that the stress must be coupled with the eigenstrain. Yes, you see. So what is nice is, from what we have discussed yesterday, if you can compute the eigenstrain of your defect, whether it is a vacancy, interstitial dislocation, whatever the defect. We're going to talk about dislocations in more detail, but if you know that by looking at how the stresses vary in the cell, as some of you have done yesterday or we discussed yesterday morning, if I know that, then for any stress tensor, I can know how the energy barrier or the enthalpy barrier will vary. And for example, for a vacancy, if delta H varies, so this term varies, the jump frequency will vary, and so the diffusion rate or the diffusion constant will vary, and I can predict it. I can predict the dependence of the diffusion constant on the applied stress by just computing the eigenstrain tensors, looking at the stress which is applied, and that's it. It's done. You see, and we have such in several instances, in particular in the case of dislocations, this approximation is an approximation, right? We have to assume that the CCC is valid. The action, at least on dislocations, it works extremely well because we can do the direct calculation of delta H, and then we compare with the prediction using the eigenstrains, and the two match beautifully well. So, yes, that works. So let's see. So I guess I've told you this. I've told you everything that is on the slide with the two conditions: stress coupled with eigenstrain, and eigenstrain varies along the. This is the initial configuration. And now I'm looking at what is happening when the distribution moves from this position to the next. And so to get the next position, it's always the same drawing with you. It's easy. I just need to break this bond here. I reconstruct it here. And I somewhat rearrange a bit the planes. And this is my final configuration. The distribution has moved by 1 interconnect distance. If I look at the energy going from the initial position to the final position, I'm going to get an energy barrier. So for now, I have no applied stress, so I have the energy as a function of the position. And I'm going to get this barrier. And in the small community of dislocations, we call that the Piles barrier. For the anecdote, just the story, which is, I don't know if you know that, but so Piles was a solid state physicist. And actually, he has his name. He didn't care about dislocations, but he was at Cambridge at the same time as Navarro, one of the fathers of the dislocation theory. And Navarro was developing his now so-called Piles-Navarro model. So again, the equations, he could not solve them. And Piles was there in the coffee room. He looked at the equation and he said, "Oh, it's easy to solve." And he showed him how to solve the equation. So that became the Piles-Navarro model. And in the Piles-Navarro model, you had a model of this energy. So it became the Piles barrier. But Piles moved on, didn't care about dislocations, and only learned many years after that there was his name everywhere in the dislocation community, whereas he just didn't. So that's the Piles bar. Right? Where did I want to say? Yes. Now, depending on the core structure and on the material, this barrier can be large or it can be very small. So as a general rule, what we observe is that and this agrees by the way with the Piles-Navarro model, if I have a core which is extended or even dissociated, like in FCC metals, the Piles barrier will be negligible. On the other hand, if you have a core which is very compact or three-dimensional, then the Piles barrier will be large. As in BCC, the screw dissociation for BCC metals has a large Piles barrier because the core is extremely concentrated, So if I am in an FCC metal, then I have no Piles barrier. And if I have a dislocation and I apply a shear stress to move the dislocation as we have discussed before, the dislocation is going to glide in an athermal way, non-commonly activated. And if you measure the velocity as a function of the applied stress, what you see is that as any thermally activated process, there is only a small dependence on temperature. So the velocity at low applied stresses, what you see when you measure the velocity is that the velocity depends linearly on the applied stress. And the coefficient here, which we call a mobility, the mobility that you measure, so the slope of the curve here, will depend on temperature, but only linearly. So a small dependence on temperature of the velocity, which is proportional to the stress. This is when there is no Piles stress. Now, when there is a Piles stress, as in BCC metals, then the motion of the dislocation from one position to the next becomes thermally activated. And in this case, we have to really look at what is if we do that, if we have a high Piles stress, then the velocity, instead of being linearly proportional with the stress, will depend on, as we have written before, so delta H. If we forget about the entropy, it's going to be delta H. It's going to be proportional to minus delta H over KT. So it means that for the dislocation, what I need to look at is not the Piles barrier in terms of energy, but in terms of enthalpies. What is the enthalpy of a dislocation? So we said, or H here, H is E, and then minus, and if I I'm going to write the initial expression because that's how we can get the result. We said that it's the energy minus sigma double contracted with epsilon dv over v. So in this case here, what is my configuration? The configuration is I have a straight infinite dislocation. So I have a dislocation segment here, which is moving from an initial position that was here to a final position that was there. And I can look at a segment of length L, for example, which moves by a distance x. You see what I mean? You see what I've done? And this would be the cut surface, right? This is the region which is cut by the Burgers vector. What is the eigenstrain of a dislocation? It has a shear component. Yes. Yeah. What did you write yesterday? So here I have the dislocation. Perfect. Very good. I have the dislocation. I have its Burgers vector, which is d, and there is the normal to the glide plane, which is n. And we said that it is b dialectic product with n, multiplied by the direct function of r that has to belong to s, to the surface, to the cut surface, dv. You agree with that? Yes. And so the cut surface would be this dashed surface here. Yes. So if I want to write explicitly, so here I have a term which is sigma double contracted with b dialectic product with n. In terms of sums over indices, how is the what is this expression? So it's a scalar, yes. It will be expressed as it's a sum over the components of sigma ij, and then multiply that by the components of. And what are these components? What is the ij component of b dialectic n? bi nj. So in terms of vector, what is this? This is, for example, I have sum over I of sigma ij, sum over I, sum over j of sigma ij nj bi. What is this? Okay, with any of math, what is this? This is the product of the matrix sigma dot n, and it's the EF element. And now I take the EF, now I do a sum over I of the EF element times B. So what is this? This is B times sigma times n. Yes, which is a scalar. Right? In terms of dislocation plasticity, or in terms of dislocations, or what is this? It's the real of surface, exactly. Right. So this divided by d to have sigma dot n dot b over b. This is the resolved shear stress. So now, what is the integral? What is the enthalpy of the dislocation? H is E minus. So I have this term here, which is a constant. So I can get it out of the integral. I have B sigma n. And then what remains? So the rest of the integral, what is it equal to? Mm-hmm. So I've taken all of this out. What remains is the integral over the volume of the direct function of r belonging to S dv. And this is equal to displacement. So yeah, so x will come. So the integral of delta x dx. This is equal to delta s L code x dx. This is f of 0. Now, if I do, for example, so with my notations for delta s is equal to x naught, this would be f of x naught. Now, this is in one dimension, so it means that in one dimension, when I put the delta x is equal to x naught, what I end up with is the value of the function only on x naught. Now, if I do in three dimensions, if I do, and I can forget about this guy now, if I do this, this belongs to S, I integrate over V, delta of x or R, V. This interval here would be zero everywhere except when I am on the surface. And the result would be, maybe it's true, it's just S. Yes, I don't know how to explain it, but the integral of the delta, because it's non-zero only on the surface. In the end, the result is the surface itself. And so in our case here, the surface is S here, and this is L times X. So what do we have? We have this multiplied by L multiplied by X. So I have so what is the enthalpy? So what's the effect? So I have this come here, and then this is a constant, right? This is a constant. And then I have a minus, and I have something which is proportional to x. So the second term here, what does it do? Actually, it subtracts to this energy here. It subtracts something which varies linearly. And so this energy profile will become, with the stress, will become something like this. If I make it even bigger, it will become something like this. And at some point, so here when I am at this stress, for example, I have an energy, I still have an energy barrier. This is the new delta H. You agree? This is my new delta H, which is here. And at some point, if I keep increasing the stress, what is going to happen? Delta H is going to disappear. And the stress at which delta S disappears is, it's called the yes, exactly. It's the pile stress. Again, the guy who didn't care about this occasion has his name on the pile stress. So what is the pile stress? The pile stress is the minimum stress above which the dislocation can move thermally without the help of thermal activation. And to move without the help of thermal activation, it means that the energy barrier has to become zero. So the pile stress is when the activation barrier is equal to zero. And we can compute it actually, or we can see here. So so I have a delta along S, so it is the pile's barrier minus sigma B sigma N. Now I can divide everything by L, right? If I define here an enthalpy per unit length, since my dislocation is straight and infinite, I have here a pile's energy per unit length, and I have this one that does not depend on it. So let me implicitly say that everything is per unit length. I remove the S. So this is the enthalpy per unit length, energy per unit length, and then the slope here. Now what I want is I want delta H. I want to have the energy barrier. I want delta H, which is what? Which is the H at the activated state minus the H at the beginning. Where defines SR here? How do I compute SR? Mathematically, for this expression, what SR will correspond to us? So you want to let X star, you do dH over dx, which has to be zero. And what is this? This is dE over dx minus B sigma N. And so I can get, so this is the result shear stress, right? So I know, so it has to be zero. So I know that x star will be the x value such that the derivative of E is equal to the result shear stress. Yes? But now if I look at, so here, yeah, if I, let me, if I, from that graph here, if I look at not E, but dE over dx as a function of x, where will it look like? Where does dE over dx look like? Yeah, it's going to be, this is positive, and then negative here is going to be something like a sinusoidal, right? This equation tells me that so the x that I have is such that this derivative here is equal to the result shear stress. So when I look, you see, so this equal that. This tells me that I'm looking for the x such that the derivative is equal to the result shear stress. So I take the derivative. I have the result shear stress at some point. So for example, initially when I have no stress, I'm here, and the intersections give me the stable and unstable positions. So with no applied stress, I have two intersections. I have 0 and I have 1/2. 0 is the initial configuration. 1/2 is the middle. As I increase the stress, I go up and up. I have the initial configuration that changes. This point would become this point. And the activated state also varies. So initially it was 1/2, and it's going to be less than 1/2. And the initial position was 0, and it's going to increase. And so I can go up and up. And at some point here, this is when the initial and activated state join. And that's the maximum result shear stress you can apply where you still have an activation entropy. And so the ideal stress is the result shear stress which is equal to the derivative of the energy with respect to x, or the maximum derivative. So this is what is very often done in the literature. You take, and this is what we have done, for example, with DFT. You draw the Peierls barrier with no applied stress. Then you look at the position where the slope is maximum. That's the dE over dx max. And that slope here is equal to the result shear stress times B. There's the B thing. This result shear stress times B. So from the maximum slope, I can get the maximum result shear stress. So this would be the Peierls stress times. You see what I mean? Am I making sense, or? Yes? So it works, but there's a big approximation here, which is that the energy here has no fundamental reason why the energy would not itself depend on the stress. If that is the case, then that approximation here, that calculation is wrong. And there are some cases where we have shown long time ago, we have shown that there are cases where the maximum slope does not correspond to the Peierls stress because of an evolution of the energy itself with the stress. Some nonlinear effects. It's not for what we have seen using DFT for critifications in BCC, that approximation works. So we only need to compute the Peierls barrier. We get the maximum slope that gives us the Peierls stress. So I have this function here. So I know that, so here it's increasing. So I know that the derivative will be positive. There's the maximum, so I know the derivative will be 0. And then here is decreasing, so the derivative will be negative. And then if you look at the curvature, here you have a positive curvature. And then here you have a negative curvature. So if you have a positive curvature, it means that the derivative will increase. When you are here, you are the maximum, and then here the curvature is negative, so the derivative will decrease to 0. And then here is going to do the opposite. It decreases and then it increases. Sorry, wait, yes, I don't know. It's so we said that, okay, so here it should be the surface swept by the dislocation. But if you go in our geometry here, the surface swept by the dislocation is the length times x. And so that makes S equal to Lx. So it depends on the dislocation. It depends on the distance between Niles valleys. They don't need to be equal to the Burd's vector. They can be small, bigger or smaller.
Cubic rotation sets. Perfect.
So edge with edge, the Niles valley is B. With edge, yes. With a perfect edge dislocation, perfect edge dislocation, the value is B. With a screw dislocation, it can be, I mean, it's usually it's close to B, but it can be like in BCC, it's a bit smaller than B, if I'm correct. And so now, you see the dependence in H dependence. So the eigenstrain depends on X because of the surface of this the dislocation strikes. So this term is constant, but you have a term which depends on the position of the dislocation because it's the area squared by the dislocation.
The object is it's like outside the higher space please at that
Okay, sure. So yeah, it will come. But at least here, yeah, so is everything clear? More or less? Yeah. So what that framework tells us is that the pyro stress is only determined through the result shear stress, right? Everything here is depends on this bubble product here, which is the result shear stress. There is no other term. So if I apply a complex stress tensor, the only term in the stress tensor that will affect the motion of the dislocation is the result shear stress. So for those who were at my seminar 2 days ago, that would apply to what type of metal? What we had just said here. Or if everything depends on the result shear stress and no other term of the stress tensor, it means that this system follows law. It follows Schmidt law, right? Schmidt law says that from the full stress tensor, only the result shear stress matters. Basically, that's what Schmidt law says. And everything we have said here, you see, we have a dependence only on the result shear stress. So that's Schmidt law. And so that typically will apply to acid materials, the good guys that follow Schmidt law. For BCC, that's related to your question. For BCC materials, that does not apply because there are non-Schmidt effects. No, I have done more. Just look what you often read in the literature is that so because we subtract this line here, we say that the stress tilts the energy barrier. So there's a tilt of the potential energy because of the work of the applied stress. And and it tilts until the barrier disappears, and that's the part. Is that yeah? Do you have questions or is it here-ish? Well, I guess that's what was on the next slide. We have the eigenstrain, we have gentle P, and we have the fact that the pound stress is there. Okay, I'm not sure I want to go. So, how can I? So, just to show you what trick about what I wanted to do initially was to tell you more about BCC dislocations. So that might take me too long. I just want to mention one thing, which is here. That connected to your question. So, as I said in my seminar, BCC metals, they are known for not following Schmidt law. And one of the reasons why it does not follow Schmidt law is that if I look at the energy barrier for a dislocation to go from one piles barrier to the next. This is a barrier, the typical barrier that I get, so the piles barrier in the Pascal. Now, on top of that motion here, what I do is I add a pure shear. So I compress in one direction and I stretch in the opposite direction. And I redo the LED calculation. So that stress tensor does not create any result shear stress on the dislocation. We could check that property here. It's going to be 0 for the screw dislocation. So with that stress tensor, if the system follows Schmidt law, then this term is 0. So the stress does not couple with the eigenstrain, and so the energy should not vary. We do the DFT calculation, and this is what we get. This is our theorem express. When we apply 600 MPa, we are here. 1.2 GPa, we are here. If we do negative, so here we see that the Piles value depends on this, or we call that the non-glide stress term. So which means that you're missing something here. So our seeing this, our idea has been to say that actually I have a dislocation. So I have a screw dislocation here. There is an eigenstrain which is related to the cut surface, the one we have discussed. This one will give you a dependence on the result stress. But then we said maybe when the dislocation is moving from one position to the next, maybe the core of the dislocation can deform. The core of the eigenstrain of the dislocation core does not need to be the same in the initial configuration or at the activated state. So what we did is we assumed, we modeled the dislocation as the domain kept, and then we added a cylindrical HRB inclusion. So a cylindrical precipitate around the dislocation core with a certain eigenstrain tensor. And then we use methods bit more tricky, but exactly the same idea. We looked at we measured the Piles barrier, and along the Piles barrier, we also measured what are the internal stresses that form using fixed parity boundary conditions. And from these stresses, as we have argued yesterday, we were able to compute what is the eigenstrain tensor of the dislocation core. So this would be a one-on-one fate, right? And assume that initially the dislocation is centered on that upward triangle. That's its initial configuration. When it moves to the next position in the next upward triangle, it will follow a certain path. Say it doesn't need to be straight. Actually, it's not straight. So the path that the core follows will be maybe something like this. Along this path, for example, when I am here, I am near the hard core configuration. There is no reason why the eigenstrain of the dislocation in the hard core is the same as the eigenstrain in the easy core. And it's this variation of the eigenstrain between the different configurations, coupled with the applied stress, that can give you not lag effects, the effect of these stresses. So we call these replicas images. And at least initially, what we do is each image here is a linear interpolation between the initial configuration and the final configuration. So it means that if linear approximation, linear combination means that the displacement, so basically if I assume that nobody moves this atom, between here and here, this atom will move by 1 neuroatomic distance. And so if I look at the linear combinations, what is going to happen is that, for example, if this one is at 1/3 of the distance, the atom here will have moved by 1/3. Here it will have moved by 2/3, and there it has arrived. And so here I'm going to have something with the atom which is here, and then here I have something where the atom is even further, and then it arrives, right? So this is 0. this would be 1/3, this would be 2/3, and here this would be 1. You see what I mean? So now you compute the energy of these configurations, and you're going to get, before relaxation, the energy of this one might be here. The energy of this one, we need another, yeah, would be on the other side here, and then relatively high. Now I want to, so I have an initial path. Like we need a third. I'm going to put one in the middle here, where the stochastic is exactly at the center. So this one unrelaxed would be maybe, right? So I have an initial energy path due to the linear combination that I can draw like this. Yes? But I know that this linear combination is not the minimum energy path. So I want to relax the energies along that path. If I do nothing and I just relax the energy of this image, what is going to happen? It's going to go back here. This one, I'm lucky because it's very symmetrical. So if I'm very lucky, this one will converge, but that's really because of the whole procedures. If I relax and take this one, it's going to go down there. So what the guys, so obviously you want to avoid that. So what the guys said is that let's put springs in between the configurations so that the configurations cannot collapse onto one another. What does that mean? It means that in configuration space, you create a spring between the position of the atom in one image and the position of the same atom in the next image. And then you do again, the position here is related by a spring to here, and then from here to here. So if there is only one atom moving, I start with my, so I will create the effective energy, which is the energy of the system, the physical energy of the system. Then I add, so I'm sorry, the total energy will be the sum over the images. So I would be an image of the energy of the image, the raw energy, which is this one. And then I will add energies of springs. So something that will look like 1/2 sum over the images of the certain spring constant. And then I have the position of the atom in the image 1 plus I plus 1 minus the position in the image x squared. You see, so this is a spring that acts in the configuration space and links the position of the atom in one cell with the other one. If when I do the magnetization, the atom, that configuration wants to go back to here, it's going to compress the spring, and then we create an extra energy that will stop the convergence. So the effect of the spring will tend to keep the distance in configuration space, will tend to keep the distance between images constant, and the images can no longer fall. I just said, I do a linear combination of the displacement, so that configuration here is not relaxed. So it's going to be of relatively high energy. And this one, not relaxed, would be also high energy, and it's just the idea that before relaxation, these configurations are high in energy, and what I want to go back down. Zero justification. It's purely numeric, and it did worse. It's super efficient, but it's worse in the sense that imagine that I have an initial. So I'm looking at the energy of the system. I assume that I have a system with just 2 degrees of liberty, x and y, and I'm looking at the energy from above. So this would be a minimum, and then I have another minimum somewhere here. So that would be another minimum, and then in between, I will have a ridge, like in the mountains. And what I'm interested in is I need it's not like this. It's I have something. I have the maximum going up here, and then along this line here, somewhere there is a configuration of minimum energy to go from here to here. But I want to find this guy. Now, when you create these images, imagine the initial, or imagine that the real minimum is here. If I do a linear combination, my initial path will be along this line here, and then I have the initial configuration. I have one configuration here, one here, one here, and the final configuration. And what I have done is now I have put springs between these edges. And I want this path to converge to the minimum energy path, which could look like this, for example. So this image should go here. This one should converge to the maximum. This one will converge here. In that minimization, actually, when you look at the forces, each image here feels the forces coming from the potential energy and the forces coming from the springs. But now, if I take, for example, the force coming from the potential energy, we can imagine that this force is, for example, it's going to be like this. This is the force due to the potential energy. And this force has two components. There's one which is perpendicular to the path, and one which is parallel to the path. The force which is parallel to the path, what it does is it tends to bring that image back to zero. You don't want this one. You only want to keep this part of the force, which is perpendicular to the path, because it is the one that will bring the path to the minimum energy. If you take the force due to the springs, it's just the opposite. The force due to the spring, there will be a force, I don't know how it is, and the image is like this. Same thing, there are two components. I'd only use this component because this would bias the potential energy. I only want to keep the force which is along the path because that's the one that keeps the images separated. So what they did is you have this effective energy, but the forces that we use, the forces are not the exact derivatives of this energy. They are the derivative of the potential energy. I put it like this, in the perpendicular direction, plus the energy coming from the springs in the parallel direction. So you use these generalized forces to drag the path down to its minimum energy. The trick or the difficulty is that since the forces do not derive from an energy, there is no reason why the algorithms that we use in labs, like conjugate gradient, there's no reason why they would converge. Because the convergence of the conjugate gradient algorithm requires that the forces are the derivatives of the energy. In the NED method, they are not. So there's a bit of luck that convergence works. That's something to keep in mind. You more or less see the philosophy, the idea? So here, these are numerical springs. So there's a numerical parameter, which is the constant of these springs. Luckily, you don't need to work too much to find a value here that will work. There's a whole range of values between, so in the units of length from 1 to 10, it doesn't make any difference. So you can put any value between 1 and 10 and you will get the same result. But there is a numerical parameter here. And the other remark I wanted to make is that for the NED to work, you have to know both the initial and the final configuration beforehand. In some cases, like a dislocation, it's very simple. Now, take a random system. You take a glass, you have a glassy configuration. You are sitting in one glassy configuration, and you want to know what is the path to go out of that configuration. Actually, the new configuration, there is no way for you to guess beforehand what will be the final configuration. You don't know that final configuration. You cannot use DN. You have to use other methods, like something called activation relaxation technique, that allows you to explore the potential energy landscape without knowing the final configuration. Right? So NED is extremely efficient. It works very well, as you will see this afternoon, but only if you know initial and final. So it means that I'm going to follow these effective forces until the effective forces are below some threshold. And what you see, if you do that, you see that the initial energy here will, so it's you're going to use you're going to like continue or fire. I think it's fire that is used in mouse. You use fire, and so iteratively, you're going to see that the energy will go down, 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 until it converges. And the path that you get is the energy barrier. So this afternoon, I propose you to look at the migration barrier over vacancy. Most simplest thing we can do is look at vacancy. Those you interested can also look at a squeeze radiation if you want. It could work the same, but it's longer because you invest a bigger cell. So for example, so I didn't have time to talk about it, but probably many of you know that the BCC screw dislocation at finite temperature, it does not move as a straight line. It forms a kink pair mechanism. So if you do NED for screw dislocations, this is the initial configuration. This is the final configuration. If you do a linear interpolation, it will correspond to a straight infinite dislocation, just moving straight. Sometimes numerical noise helps you, but in many times, actually, when you do the relaxation, the dislocation remains straight. You don't see the kinks. So if you want to see the kinks, you have to put them in the initial path. And so one way that we have been using is, instead of using a linear combination of all the positions, what we do is we have the initial configuration, we have the final configuration, and now the image, we build it by taking the position of the atoms in the initial configuration in some region. And then in the middle here, we take the positions from the final configuration. And the size of that region, we make it bigger and bigger as we go from one image to the next. So that will create double kinks, badly relaxed. I mean, not relaxed at all, but it will create a double kink that expands along the dislocation in the initial path. You relax, and then you get a nice nucleation and propagation of the kink. With NAMS, what you can do is you can build your own path, and then you can read it as a little bit of the NED, and that's how we do it. Oh, but I wanted to mention is if you want to go one step further. So here, the NEB, as I explained to you, works with the cell shape is the same in all images. If, for example, you want to look at the energy barrier of a phase transformation, going, for example, from a tetragonal to a monoclinic cell, then the shape of the cell itself has to vary along the path. And so what has been done is to add strings between the images, but also between the vectors of the simulation cell. So the vector in one cell has springs connecting it to its position in the cell before and in the cell after. So you have another fictitious term here. You do the magnetization also over the atomic positions and the cell shape. This is called a solid state NEB, and it works fine. It works very well, and you can look at phase transitions using this. Yes, because the volume of the BCC and FCC are not the same. So you have to if you do linear, you could do a linear approximation, but then the size of the cell will increase linearly and will not relax. And that can lead to bad, wrong results. So you have to use the SSNEB, the solid state NEB, to allow the shape or the volume of the cell to change. It's called, you have the name which is given is solid state NEB. Yeah. So yeah, solid state, so SS. Yeah. There's a version just before I forget. Yeah, so if you use solid state NEB, there is a version not the lamps, but it's with ASC, I think, or if you type SSNEB lamps, it will give you a package. Be careful. Those calculations only are, they are, because there are mechanicians in the room, I can say it. They are correct only in the small deformation limit, because because you have to compute an energy which is associated with the deformation. So for that, you have to compute a stress times a strain, and both have to be coherent between one another, and they are using variable stress with the simple linear strain, and both are not conjugated. So what you should use is like the first or second character of stress and some finite strain measure, which is not in the basic version. So those who are hardcore mechanicians, be careful, this is wrong. You have to correct for it. But that was a very technical, say the scientific, just to give you a bit more. Yes, that's okay. So what you have to do is you have to have your separate routine outside of LAMMPS to create the initial path. And then you can have LAMMPS read your initial path. LAMMPS will not, so for example, to create the double kinks, LAMMPS cannot create double kinks for you. LAMMPS can only do linear interpolation between initial and final. So you have to have your own code to prepare the initial configuration and then you delete LAMMPS. Yeah, no, I'm sure because we have used it. I'm just trying to look for an example. I think maybe somewhere. I need to find the right one. You see what it's total, no. Oh yes. Yeah. MEB each, and then these are the five that are right. There are 4 in titanium. I don't know. You have to. I don't know what the activated state is. Not even sure this is NEB. I don't know. I can look for it if you want to, but yeah, I don't know what is the activated state between DCC and SCC. I can show you, in zirconia if you want. I can show you in zirconia a path, but I can show you the path from tetrabundle to monoclinic in zirconia. But for the Bain transformation, I don't know.